All right, so to wrap things up in this section, we're going to talk some more about this indicial equation. So we ended the last video by showing that for any given DE, we can find, let me back that up. Any DE to which we would be applying this method. So a homogeneous second order linear DE where we're finding a series solution about a regular singular point. We can find the indicial equation for that using this little guy right here, where R is what we're solving for, that's the unknown. A naught and B naught are the first terms, respectively, of the two series expansions for little p of x and little q of x. Now notice, because it's a series and we're just looking for the a naught term or the b naught term to use in that indicial equation, those are the constant terms in that power series. You can always obtain that constant term by plugging a 0 in for p of x, because all of these other terms will zero out. And same thing here. So a naught is little p of 0 and b naught is little q of 0. That's how we find those. Okay. Now, on the next page, we're going to talk about 3 cases that we have to consider for these, but it's not going to matter for you a whole lot because the only problems I'm giving you for homework, the only thing I would ever test you on is the first case, and I'll talk about why once we get to that point. But I want to talk a little bit more about this indicial equation first. So let's go back to the previous example, the one that we just did. This guy right here. Okay, I'm going to rewrite that differential equation. It was 2xy double prime plus 5y prime plus xy equals 0. So let's suppose that we were redoing that example, but now we knew what an indicial equation was and we knew how to find it. How would I go about finding that indicial equation before going through all of the work that I did on that page? Well, let's see. So first thing I would need to do is put this in the correct form. Divide everything by 2x. So y double prime plus 5 over 2x y prime plus x over 2x, which is equal to 1/2 y equals 0. Okay? And you can use this form to also verify that x equals 0 is in fact a regular singular point. But what I want to do is find little p of x and little q of x. Remember, this guy right here is capital P of x. And that 1/2 right there is capital Q of x. So what is little p of x? Little p of x is equal to x times capital P of x. That's how we defined it earlier. And that would be equal to x times 5 over 2x, which is the same thing as 5/2. Okay? Q of x is equal to x squared times big Q of x, which in this case is x squared times 1/2, or 1/2 x squared. Okay, and remember, the reason for finding this little p and this little q are to be able to find these terms, a naught and b naught, so that I can find my indicial equation right from the beginning. But according to what we said here, we can get that a naught and b naught by plugging 0 in to little p and little q respectively. So this is equal to p of 0. P is a constant function, so p of anything is just going to be 5/2. And then q of x, if I plug in 0 for that, that's going to equal b naught. So b naught is equal to q of 0, which is equal to, I can see that would be 0 in this case. And so that means my indicial equation is equal to, according to this up here, r times r minus 1 plus a naught, which we said is 5/2 r, plus b naught, which is equal to 0. And we set that equal to 0. Okay, if I want to clear that denominator, I can multiply everything by 2. So I have 2r times r minus 1 plus 5r equals 0. And then if I distribute that 2r in, I'm going to get 2r squared minus 2r plus 5r, which is the same as plus 3r equals 0, or equivalently, r times 2r plus 3 equals 0. That's the same indicial equation that we found right here. But I didn't need to do all of that work ahead of time to find it. So at the very beginning of that problem, I could have gone through this work, found that indicial equation, and then found the values for R1 and R2 that I would have wanted to use to find my solutions. That doesn't mean I get to dodge all of this stuff up here, because we still do need to find our recurrence relation, which comes from this. But essentially what that means is that when I removed these terms from my series here, remember, I had to remove 2 terms from this series, 2 terms from this series, and they're all showing up right here. The only thing that those were used for was to eventually get to this indicial equation. After that, all I needed was the recurrence relation. So what that means is if I find my indicial equation first, once I pull these terms out, I can just get rid of them. I don't need to use them anymore. And all that's going to matter after that point, for this work at least, is going to be that recurrence relation. Okay? So that's a little bit on the indicial equation, but I mentioned here that there's 3 different cases that we talk about. And because this indicial equation, you could see, is going to be a quadratic equation in the unknown r, in general, quadratic equations always have 2 solutions, counting multiplicity, which means we might have 1 repeated real root, but at most 2 solutions. And we're going to break this down into 3 cases. It's not going to be the same type of 3 cases, though, that we saw back in 4.3 for solving homogeneous linear second-order DEs with constant coefficients. The 3 cases are as follows. So we might have a repeated real root where R1 is equal to R2. And in that case, the Frobenius method is only going to give us 1 solution, 1 series solution, which is not good because it's a second-order DE. We need 2 linearly independent solutions so that we can form a fundamental set of solutions and get our general solution from that. So in that case, we only get 1 series solution and we have to find another one somehow. Another thing that occurs is if the 2 roots of your indicial equation, R1 and R2, are distinct, so they're not equal to each other, but they differ by a constant. We're not going to go through the process of showing this, but once you do that, if you get those 2 different roots that differ by a constant, what's actually going to happen is the 2 series that you get as a result from that are equal to each other. They have the same terms, and really, even though it looks like you found 2 series, you actually only found 1 in that case also. So you're still tasked with finding a second series to find a general solution. The other case, which we're actually going to be calling that case 1, this last one here, is where the 2 roots of your indicial equation are distinct and they do not differ by a constant. That's what happened in our case, because if you remember from our indicial equation, the 2 roots that we found were 0 and -3/2. Those do not differ by a constant. So we got 2 linearly independent series solutions, which is what we need for a general solution. I'm going to break those 3 cases down on this last page here. Okay? So again, suppose that we have a linear homogeneous second-order DE with a regular singular point, and we're specifically thinking about x equals 0 as our singular point. And let R1 and R2 be the indicial roots. We're going to suppose that both R1 and R2 are real numbers. Remember, solutions to DEs can be complex, but for this, we're assuming they're real. And that R1 is greater than or equal to R2. Okay? So in the first case, which was actually the last one that we talked about on the previous page, if the 2 roots, R1 and R2, are distinct, and if R1 minus R2 is not an integer, so that's like the previous example that we did, then the Frobenius method will produce 2 linearly independent series solutions, which we could use to form our general solution. And it's important to note here that both C0 and B0 in these series are non-zero. The reason for that goes back to that example that we did. Remember here, we had to assume that C0 was not equal to 0 so that we could get our indicial equation in the first place and then solve that. Okay, so case 1 is the one that we looked at. That's the example that we looked at. Case 2 is where R1 and R2 are still distinct, but this time they do differ by an integer. If that's the case, then there still do exist two linearly independent solutions, but only one of them will come from Frobenius' method. The second one is going to take this form. Some constant, which you have to find, times y1 of x, which is what we got here, natural log of x, plus another series that takes the form of what you would expect to find in Frobenius' method. Okay? I'm not showing here or right away where this term comes from, but I'll mention where it comes from at the end. Okay? It is possible that this term c can equal 0, which would cause this entire term to go away, giving us a series that looks like it would have come from Frobenius' method. But in general, we don't always get that second series, and so this term might show up. If R1 and R2 are equal, which means you only have one actual root in that indicial equation, then Frobenius' method will give you this series, and it says, x to the n plus r1. I could easily replace that r1 with r2 since they're equal, but you get the idea. And then you'll get a second solution that will take a form very similar to what we have up here, but we lose that capital C. And because of that, there's no chance of this term becoming 0. This will always be present here, whereas here, if C is equal to 0, this term will disappear. Okay. Now in cases 2 or 3, that solution, y2, which has this complicated looking form in either case, can actually just be found by using reduction of order. Remember, that's what we used reduction of order for all the way back in section 4.2. You have a second order linear DE, homogeneous, and you're trying to find a second solution having already found one. And you want that second solution to go together with the first one to make a linearly independent set. And we show that this formula, which is what we're calling reduction of order, always produces a second solution which satisfies that. We're just applying reduction of order in case 2 and case 3 to produce these equations, these solutions. So that natural log of x that's showing up in here, it's not just a random thing, it's a natural thing that pops out of this formula. Now, I am not doing any more examples in this section. We're not going to look at any examples where case 2 or case 3 happens, and you're going to notice in your homework, you're not dealing with any of those either. And there is a good reason for that. Think about what it would take to evaluate this. Remember, y1 is a series, right? And y1, we're actually integrating a function that has y1 squared in its denominator. How do you do that if that's a series? Well, it would involve evaluating this term up here and then doing long division with that series down there and then integrating term by term and then multiplying that series to that series. I mean, if you already thought that these problems were long and tedious, I mean, that's far worse. And in fact, your book even tells you that to do the work on reduction of order for finding this second solution here, in general, it's a better idea to use a computer algebra system, or a CAS, that's what they call it. And so if you look at the homework problems, the ones that I did not assign, that have that deal with case 2 and case 3, it'll say use a computer algebra system where necessary. I'm not assuming you have access to one of those, so I'm not requiring you to do that. But I did want to talk through these 3 cases so you're at least aware of them, and that you know that Frobenius' method is only guaranteed to give us 2 linearly independent solutions in this case, which is what our first example looked like. But since we're stopping here, that's going to be it for Chapter 6.